record. And 1 second, my speakers are not working. Can someone unmute themselves and say something?
Hello. What exam are we going to work on?
Is anyone unmuted and saying something and I just can't hear?
Yeah.
Okay, I guess if you guys are talking and you can't hear me, I don't know why. Odd. Hello, everyone. Oh, it's good to see your faces. I'm gonna check them real quick and then we'll get started. Just because if I can't hear your questions, it's gonna make life a little bit difficult.
Wait. Oh.
So real quick, as a reminder, if we're talking about okay, can someone say something again?
Hello.
Yeah, okay, good. I can hear you guys now. Yay.
What exam are we going to work on?
What?
What exam are we working on?
We're going to work on the one that says actual exam from last year at this time.
Okay.
All right, so
yeah.
Again, it's good to see all of you. Some of you I know, some of you I'm meeting for the first time. All right, so before we get started, just a couple of things. Yesterday, particularly those that are joining us for the first time, right? Remember, if you're going through IR, what does IR show us at its very simplest?
Functional groups.
Functional groups, right? IR should be treated as something that tells us functional groups at its very simplest thought, all right? Because it basically shows us bond energies. The other thing, right, is that we want to make sure that we know when we are doing nomenclature and we're naming things. What was the one thing I told you guys to do that would help your scores?
Oh, wasn't it just start from the end and then work your way?
Well, that's the basic thing in nomenclature, but what was one thing you could do to your drawings to help you?
Didn't you say to like put as much as we knew?
As much as you knew and number your carbons. That way, whoever's grading your exam can see this is how they are numbering their molecules, right? And if you do those basic things, the more information you provide for your grader, the easier it's going to be, right, to grade your stuff and give you more points. It's a very tidy room there, Bella.
I don't have much in it, so.
It's okay. You're a small person. You don't need a lot of space. It's okay.
I don't.
All right, so let's go to share screen. Okay, and we're going to work through all of these problems. And so if you have to dip out, I'm recording this and I will upload it to YouTube. I still need to upload yesterday, so you can go back and check these videos for stuff. But remember, we meet every Thursday. So if you want to come at any point, maybe I'll expand it to 2 times a week to help you guys out if you really need it, because I don't have a lot of stuff to do right now because of quarantine. Because I live in a state that properly does quarantine and our death rate is extremely low and we can go places because we stay inside and wear a mask everywhere. Okay, draw the Lewis structure showing all lone pairs and non-zero formal charges. So go ahead and do that cyano group, cyanide, CN minus. Go ahead. As you're doing that, I'm going to pour myself a drink of water. But remember, when you're doing your groups, right, your molecules, you want to make sure that the charges of all the atoms, right, equal up to that total charge. We've been through Lewis diagrams before. I'm going to go grab a drink of water. I'll be back while you guys are working on that. Actually, do A and B, and we'll talk through A and B. remember the key rule that when you're doing your Lewis diagram, octet rule, unless explicitly told not to. Octet rule rules over all. Octet rule, octet rule, octet rule. Okay, so carbon and nitrogen. How many valence electrons does carbon have? Carbon has 4, right? Nitrogen has 5, and for every minus charge, you add 1 more. So I have 10 valence electrons, correct? So the proper thing for this, draw a carbon, draw nitrogen, right? And we are going to connect a bond between them. Normally what you want to do is that you want to add electrons to the outside, right? So we've used 2, minus 2, we have 8 left. So then you would say 1, 2, 3, 4, 5, 6, 7, 8. You add a lone pair like that back and forth. So we've used all 8 valence electrons. So we have 0 left. But what's wrong with both carbon and nitrogen in this drawing?
They're neutral. And shouldn't one of them have a negative charge?
They're not neutral. They created the biggest sin that I told you not to.
They don't follow the octet?
They do not follow the octet rule. For those asking, this is the practice exam from February 2020, or the actual exam. So I take one of the lone pairs from a carbon, and now I'm going to turn it into a bond. All right, actual exam under 1. So now nitrogen has a full octet, but carbon does not. So then I do the same thing, except now with nitrogen, I take another lone pair, and I take that lone pair and I turn that lone pair into a bond like this. So now carbon and nitrogen each have 8 electrons. This is correct. And so the formal charge for nitrogen, formal charge, right, is going to be number of valence electrons, which is 5 for nitrogen, minus the number of bonds, 3, minus the number of lone pair electrons equals 0. Formal charge on nitrogen, 0. I do the same thing for carbon, 4 valence electrons, minus 3 bonds, minus 2 lone pair electrons equals -1. This means the charge on carbon is negative. So add them up, 0 plus negative is going to be negative. This is correct. How'd you guys do on this one? Where did you make your mistake, Gwen?
I think what stumps me sometimes is I put the charge on the wrong atom. I put on the nitrogen just because of how it was initially written.
Well, don't forget to do your formal charge calculation, right? So remember, formal charge is number of valence electrons for that atom, minus the number of bonds, minus the number of lone pair electrons. Also, if you remember when I tried to beat this into you guys last year, this is where it's helpful to remember what each atom likes to have. Nitrogen with 3 bonds and a lone pair is always going to have a 0 charge. Carbon with 4 bonds is always going to have a 0 charge. Oxygen with 2 bonds and 2 lone pairs is going to have a 0 charge. So once you differ from that and you go into something different, that's when you realize, oh, this is different. This one should be the correct one. All right, and so you'll start recognizing that. So then we go to NCS, right? So again, nitrogen has 5, carbon has 4, sulfur has 6, and that negative charge tells me I have 1. So 5, 4, 1, 6 is going to be 16. If you have one of these complex molecules like this where you have multiple atoms, draw your atoms in the order that they give them to you. All right. If you don't recognize what it is, like if there's no symmetry or something like that, draw them just like they give you. So nitrogen, then carbon, then sulfur. So I'm going to go nitrogen, carbon, sulfur. So I connect each of them with a bond like that. So I've used 2 bonds, so that's 4 electrons. I have 12 left. Now I'm going to fill out my outside atoms first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used all valence electrons. What's wrong with this drawing?
Carbon does not have a full octet.
Correct. Carbon does not have the full octet. That is your biggest crime you have to watch out for, right? So I'm simply going to do the same thing where I'm going to take one of the lone pairs from the outside. So select on the nitrogen here. If it lets me erase it, maybe yes. And then I'm gonna make it a bond. There's only 6 electrons there, so I'm gonna repeat this again, this time from sulfur. And do that. And now have I met my octet? Does each atom have a full octet now? Yay or nay? The answer should
Yes.
be yes. Every atom has a full octet right now. So now, how many bonds does carbon have? 4. I know carbon wants to have 4 bonds. So if it has 4 bonds, I should know, commit this to memory, should be a 0 charge. Sulfur is below what atom on the periodic table?
Oxygen.
So it should have the same bonding pattern. So what did we say for oxygen was its ideal bonds and lone pairs? 2 bonds, 2 lone pairs. So sulfur has 6 valence electrons minus 2 bonds minus 4 lone pairs. Sulfur is going to be 0. Nitrogen, we said, likes to have 3 bonds and 1 lone pair. This nitrogen does not have that. So this is where my charge is going to come from. So nitrogen has 5 valence electrons minus 2 bonds minus 4 lone pair electrons equals -1. Negative charge on the nitrogen. You can draw this another way because this is a valence structure. This one has resonance. So if I wanted to draw it a different way, I could draw nitrogen triple bonded to carbon, lone pair, single bonded to sulfur. I know just because I'm an old man with a lot of experience that this sulfur does have a negative charge. So question for you, which one of those is preferred? Or are they equal?
I mean, shouldn't they be equal? Because like resonance structures, like at the end of the day, the molecule is gonna look something in between it.
That is correct, but resonance structures can have a preferred one.
Oh, okay.
If you have to have a negative charge, what atom does it want to go on? What was our rule that we learned about way back when?
The more electronegative one?
Correct. Nitrogen's more electronegative than sulfur. I don't expect you to have that memorized, but if you drew the resonance between both, you would probably be okay. Questions on this one?
Can you bring this out here? You can. Do you think I can?
What are you saying? I can hear you.
Sorry.
It's okay, no worries. Okay, next up, draw a valid resonance structure with curly arrows for each. Okay. How are you guys with mechanisms and drawing resonance arrows? Are you guys dicey? Okay, I'm going to teach you Terry's quick rules about resonance drawing. These are my rules that I use. If you follow my rules, you will get these right 95% of the time. First and foremost, what are the only thing you are moving? What's the only part of the atom molecule you are moving?
Electrons?
Electrons. You are only ever moving electrons, which appear in the form of lone pairs, double bonds, triple bonds. If we are doing resonance, what's the one thing we don't move?
Single bonds.
Yes, we do not move single bonds, and I'm going to change the color on that because our single bonds, our sigma bonds are essentially the color of they are like the base skeleton of our molecules. So we don't want to rearrange that, okay? So single bonds we do not move, but we can move lone pairs. Now, if I draw an arrow, which arrow is correct? I'm gonna give you an example here, and this is just my general rule. I'm gonna draw a green arrow, and I'm going to draw a blue arrow. Which one of these is correct?
The green one?
The green one. When you draw an arrow, right, you have to start. So where your arrow starts, it has to be an electron source. Energy always goes downhill, remember? I always said that organic chemistry and chemistry is the frat boy of sciences. It always tries to do things the easiest way possible. Energy always goes downhill. So when you draw an arrow for this, as I erase this stuff here, whenever you draw an arrow, you always start at whatever the source is like that. Always start at the source. Always start at the source. And your arrow points to where it's going. It could be going onto a bond. It could be going onto the atom, right? So the tail is where it starts. That's your second rule, right? Is that your arrow always starts where your electrons are and go to where they're going. The third rule, and this is the most important one to make sure that your resonance has been done correctly, or even mechanisms when you get there. We always conserve what? Do you guys remember from what your professor told you?
Is it the charge?
Charge, that's correct. You always conserve your charge. Charge is always conserved. So in A, right, what's the overall charge of that starting molecule?
+1.
+1. When I draw my resonance structure, what should be the overall charge?
+1 as well.
+1 as well. All right, so always make sure. I'm going to give you an example of this. It's going to look a little counterintuitive, but this is true. So imagine I have this wonderful ketone here, like this. This is acetone. If you've had lab, this is what you use to clean your glassware. I can do a resonance where I move this double bond up onto this oxygen like this, all right? So now when I do this oxygen now has 3 lone pairs. And this oxygen has a minus charge. This carbon has a plus charge. Did I conserve my charges? What's the charge of my starting molecule before I did the arrow pushing?
It's neutral.
It's neutral. What's the overall charge after I did my arrow pushing?
Neutral.
It's still neutral because I have a positive and a negative, and when I add them up, it's still 0, right? So I can still have charges if I was neutral before, but whatever the overall charge is still has to be the same throughout. Does that make sense? So if you always start your electrons at an electron source, if you always have your arrows moving from source to wherever they're going, and if you always watch your charge, if you do those 3 things, you're going to be right about 95% of the time. There's 5% every now and then where you have to know what you're doing exactly, but if you do those big 3 things, you should be fine. When we get into mechanisms, I'll add 2 more rules to that. That'll help you do it. But if you can do that. So if you guys want to try 2, I'm going to scroll down so you guys can see it. And then you guys can try 2 if you haven't already done it yet. And again, this is just so that you guys, so if you want to try, let's try A, B, and C. Don't do D yet. So remember, if you're making a mistake right now, that's fine. You're with me. This is 0 stake. Make the mistakes now. Learn from them so tomorrow you rock your exam, right?
I actually have a question on it because like I'm not really sure what should be moved in the first place.
So let's think about the first place. What can move? What did we say can move?
The only 2 double bonds that we have. Those are the only things I can
Okay,
move, but,
so we can only move double bonds, right? So I can move
Mhm.
this green double bond. It helps if I turn on the writing tool, I suppose. I can move this green double bond, or I can move this double bond. What is a rule that always has been true for about most anything we've talked about? What's the one rule when we were doing our structures that we always had to make sure we were following?
the octet rule.
The octet rule, right? So I cannot break the octet rule. So think about if I move a double bond, am I going to violate the octet rule any place? Think about that, Melissa. See if that helps you.
Wait, so are you saying that you can't, so in this case, you wouldn't be able to violate the octet if it was already in place?
Yeah, so I can go under the octet rule. I just can't go above it, right? I can have 6 electrons, but I can't have more than 8.
Okay.
Because there's no space for it.
Okay.
It would be like if one of you wanted to move a king bed into your dorm room. It's just no room for it. Or you just have nothing else in the room. I'm just imagining Bella on a king bed, just like so much room all spread out. Like those pictures when you see those small little dogs like on beds, like giant beds. Okay, so when we do this first one, right?
Mhm.
If I try to move here, can I move there? Can I move my bond over? Is there any room for it?
No, because there's a hydrogen that's not shown there.
Remember, when I do resonance, I can only move double bonds, triple bonds, or lone pairs, right? So if I was to draw that after I moved it, this is what my structure, and that happens sometimes for some reason, and I don't know why. But if I was to draw this after I drew the resonance structure like this, if I can't move anything else, right, there's a hydrogen here. So how many bonds does this carbon have right here?
5.
5. That's what we call a Texas carbon. It's bigger than it's supposed to be. So I can't do that because remember, what's the only bond I can't move? I can't move any single bonds. I can't remove anything from that carbon to make room. So I can't move that first one. This first one is bad resonance. It doesn't work. It's nothing there. So that means then this makes my life easier because typically, remember, if you looked at Dewis's PowerPoint, she had those things to watch out for when you know resonance can move a double bond adjacent to a carbon with a plus charge. If you have that, that's something to watch out for. So now this is going to move here. And now this carbon that lost the bond is going to be my plus charge, like that. Remember, charges alternate carbons. How did you guys do on that one? Good?
Were the first double one would still be there, right?
It's, oh yeah, sorry.
Okay, sorry, I just want to make sure because I was like, yeah, I think it should still be there. So I was like, I don't want to like miss anything. So yeah, thank you.
It flew away. It heard you talking shit. It's like, I'm out. Okay, try and do B. I have a sub rule for B that applies that you should always do. What do you guys think my sub rule is? There is no benefit. It's just resonance. It's there. Does that answer your question, Matthew? It's basically, remember, it's what Melissa said, is that resonance, it's not like both of these molecules exist at the same time, right? They're not alternating. It's just like an average between them. Remember, Lewis dot diagrams are really bad at showing resonance. They're really bad at it. That's why you have to draw multiple ones. So you're not actually seeing the real picture. So B has a sub rule that I always like to tell my students to do. Does anyone know what that sub rule could be for B? It's one thing that would make your life easier. If you have an atom, draw the lone pairs if there are lone pairs there. Like that. How's it going, Max?
Pretty good. I'm eating cake.
Did you bring
It
enough?
was-
Did you bring
it was
enough for
one-
your friends?
Yes, it was today. Well, tomorrow's one of my roommates' birthday. So, and he's going to Phoenix, so we decided to do it tonight because he won't be here tomorrow. So
That's nice of you. I want cake.
we have like a lot, and it's homemade. So
But you're all the way in Flagstaff.
You literally said cake, and now I'm like really wanting.
I'll like mail you some.
Oh, no, thank you. I'll just DoorDash some cheesecake from Cheesecake Factory. That'll make my life easier.
Ooh, that sounds good.
Or actually, I'll go get Jenny's. I like Jenny's ice cream. That's pretty good too. It's a local ice cream. They're from Ohio, but they have them out here and they're really good. Okay, so here, right, I can only move, if I try to move my double bond any direction, that's not going to help me, right? But what I can do is if I do this, move a lone pair here, and then this double bond has to go onto the carbon. This carbon is a minus charge. This oxygen is now a plus charge. I started neutral, I ended neutral. How did you guys do on that one?
Bad.
Okay. You did poorly, but not bad. Bad's in reference to good or bad.
I like moved the double bond to the oxygen.
Can oxygen violate the octet rule?
No.
Nope. So that's why this is the only way that can do it.
I just forgot to draw the lone pairs.
Yeah.
So-
Okay, that's fine. So this is something that we should remember now for the next one. You'll know to do that. So this is how you do B. All right. So let's try C. Draw any lone pairs that may be present. Okay, I'm going to do one thing to help you out. I'm going to draw the lone pairs. We have a lone pair on the oxygen, right? So 1, 2, 4, and there's a lone pair on the carbon. If a carbon has a negative charge, it has a lone pair. See if that helps you. How you guys doing? Don't panic. Get through this. Ellie hasn't offered to bribe me yet. Thought I would have received that text by now. But I feel offended that she only offered me like $5.
And a nice candle.
Oh, well, my bad. Sorry about that. If I did take a test for someone, I could give you the exact percentage you wanted. So if you said give me an 85%, I would get an 85 on your test. My favorite thing to do, and you guys know, is when I would take the test while you guys took yours, and I would finish it in 2 minutes. Okay, so here's a good rule that you should remember. Where should you start? Hell yeah, it was evil. It's great. Where should you start? What did I say about electrons? Which direction do electrons go? Downhill or uphill? When I think about energy, energy always goes
Down.
down. So should I start at the neutral atom with a lone pair or the charged atom with a lone pair? Charged. If I can go from negative to neutral, I should start at negative. If I can go from neutral to positive, I should do that. Always go downhill, negative to neutral to positive. All right. So what I'm going to do in this case is that I'm going to go to here like this, and then I'm going to go to here like that. So I'm going to end up with, yay, Melissa, see, you got it right. So then I'm going to end up here.
It was only after you drew the lone pairs in the carbon, but yeah, I think that like now I'm starting to get it a little bit more.
Okay, so now what am I missing from my drawing?
The charge.
Charge, right? Charge always must be conserved. So now it says to circle the major resonance contributor. So is old lefty my major or is old righty my major? what did we say if we can't tell any difference? If we have to have a charge, where does that charge want to be? On the what atom?
The most electronegative.
So which atom is more electronegative, carbon or oxygen?
Oxygen.
So that's it. Does that make sense for figuring out which one is your best one? If you have a choice between a molecule that has a charge versus a molecule that has an empty octet, you always go for the full octet first. Octet takes priority. Then you worry about charges like positive, negative, and all that good stuff, right? Octet trumps all. Okay. Using the following structure, draw a line bond stick structure. So draw your chain. We have about 3 minutes left on this time thing. So when we're done, we'll pop out, take a 2-minute break with this one, and then we'll come back. I'll open the thing, we'll start again. So go and do this one. I think we can get through this. Gonna fill up my water bottle. I forgot to fill up my Brita pitcher before I left, so I only got a little bit of water. I don't remember who it was, but someone in the class gave me this sticker, and this is on my water bottle to this day. And I love that girl who gave it to me because I really appreciated it. It says Ben Wyatt, human disaster from Parks and Rec. So she was in the 11:30 class, and she sat to my right, about halfway up. She sat right in front of the girl that asked all the questions. If you were in the 11:30 class, you know who I'm talking about. I can't remember her name.
Sarah.
No, Sarah Patowski asked good questions. This student asked bad questions. I like Sarah. I really enjoyed Sarah. She was a good egg. Okay, so since we have about 2 minutes left, I'm going to draw the structure. If you're going TL, please wait till I'm done. That is your structure right there. So the CH3 are going to be these bad boys. That CCH is going to be these 2 carbons. It's right here. This CH2 is this CH2. This CO is this CO. This CH2 to CH is here. This CH3 coming off is this. And then this CH2, CH3 are these ones. Do you see all of those? How did you guys do on that one? Good, bad? Make a mistake? Okay, we'll talk about it when we come back, but this is that first one. So we'll take a break, come back in 2 minutes, I'll reopen the room, and then we will continue on, okay? I am here for the long run. I forgot double bonds existed. We all do, buddy. We all do. I'll be back.